Building your own artificial intelligence model from the ground up sounds like the peak of technical independence. You write the code, feed it the data, and suddenly you have a proprietary digital brain. That is, until you receive the bill for the computational power. Following the release of ChatGPT, a distinct trend took hold across the corporate world. Businesses and enterprises assumed they needed to build their own large language model to remain competitive in a shifting market. Some have already done it. Bloomberg GPT is a specialized model engineered specifically to process and generate insights within the complex world of high finance. To see what that effort actually requires, we can use Meta's Llama 2 as a benchmark. It provides a clear look at the physical and financial demands of modern AI. This chart shows how those computing hours translate into hard costs. Training a 70 billion parameter model like Llama 2 requires roughly 1.7 million GPU hours. At current market rates, renting that time costs millions. If you buy the hardware and build a cluster of 1,000 top-tier graphics cards, the bill for the equipment alone clears $10 million. Once you factor in the electricity needed to run them for weeks, the energy bill reaches 6 figures. Knowledge of the underlying code is useless without the capital required to power it. This multi-million-dollar financial floor effectively restricts model building to the largest organizations on Earth. If you have the budget, you enter Stage 1, data curation. These models require a knowledge base of roughly 1 trillion words. That is equivalent to stacking 1 million full-length novels or 1 billion individual news articles. Gathering this volume of text usually means scraping the internet for public forums, digitized books, scientific journals, and massive references like Wikipedia. Alternatively, you can use an existing AI to generate synthetic data for your new model.
Researchers at Stanford use this method for their alpaca model, using an existing LLM to produce structured training examples. But this is a bottleneck. Machine learning follows a strict rule: garbage in, garbage out. Internet data is full of toxic forum posts, redundant code, and false statements. If that text isn't filtered, it will corrupt the entire model from the inside out. While much of the raw data is public, the extensive human and computational labor needed to sanitize 1 trillion words is its own massive investment. You're paying to clean the data before the training even begins. Stage 2 is model architecture. Once you have the data, you need a framework to process it. In modern AI, that structure is almost always a transformer. The core of a transformer is the attention mechanism. It allows the model to learn how words depend on one another. By drawing mathematical links between bat and baseball, the system determines word meaning based on the surrounding context and its position in the sentence. This framework is split into 2 halves. The encoder looks at the entire sequence of text at once, translating raw tokens into a deep mathematical representation of what the sentence actually means. Then there is the decoder. The decoder is blocked from seeing the future text in a sequence. It uses masked attention to strictly predict the next word, one at a time, making it the primary tool for text generation. How engineers arrange these blocks determines exactly what the AI will be capable of. It is a blueprint that must be finalized before the real money is spent on the training process. Stage 3 is training at scale. Here, the curated data is pushed through the architecture. It is the most computationally expensive part of the entire lifecycle. On a single consumer computer, this would take lifetimes. To finish in weeks, you'll have to network together thousands of high-end graphics processing units. This illustrates 3D parallelism. To keep the data moving, engineers break the model's math and the training data into smaller pieces, distributing them across thousands of GPUs working in parallel. This process is volatile. A mathematical error called an exploding gradient can cause a sudden spike in training loss, ruining weeks of work. When this happens, engineers must roll the system back to a saved checkpoint and restart. Training an LLM is not a set-and-forget process. It requires weeks of actively monitoring a $1 million engine that can break down at any moment. Finally, there is evaluation. After spending millions on compute, the model must take standardized benchmark tests to prove it is actually functional. These tests cover everything from grade school math to history and common knowledge. Testing a text generator against a multiple-choice exam is surprisingly difficult. Evaluators must use specific prompt templates to force the AI to output a single gradable letter, like A or B. But for most businesses looking for an AI solution, this entire four-stage gauntlet is unnecessary. This is the alternative: fine-tuning. Instead of building from scratch, you take an existing base model that has already been trained on the world's data. You then feed it a small, specialized dataset. The model adapts its vast knowledge to your specific needs in a fraction of the time. Building a large language model from scratch is a resource-intensive feat reserved for the frontier of technology. For everyone else, fine-tuning provides the same utility and competitive edge for a small fraction of the cost.